Hello, student. Welcome to the statistical mechanics chapter. So, in this class, I'm going to derive the expression for Bose-Einstein distribution. In the last class, I derived the expression for Maxwell-Boltzmann distribution, and now I am going to derive the expression for Bose-Einstein distribution. So, these are the characteristics of the Bose-Einstein distribution. So the first point is that the particles are identical but indistinguishable. So here the particles are identical but they are indistinguishable. And the state can be occupied by any number of particles. So this is the classical idea written by the Bose-Einstein distribution. So actually, same law is was adopted in the Maxwell-Boltzmann distribution, and because of that reason, it is a classical idea, but still it is used in the Maxwell-Boltzmann Bose-Einstein distribution. And next point is that uh, these are the particles with integral spin. So in the Bose-Einstein distribution, only the particles which are having the integral spin are considered. The examples are photons, phonons, magnons, mesons, etc. As you know, photons means it is the quantized packet of energy, light energy. They are called as the photons. And phonons means the thermal waves. The energy of the thermal waves is also quantized in small packets of energy. They are called as the magnons. And similarly, the energy of the magnetic field is also quantized, that is called as magnons. And mesons are present inside the nucleus, which helps in conversion of proton into neutron and a neutron into proton. So these are the examples for the Bose-Einstein distribution. And next, fifth point is that internal energy at absolute zero is taken as a zero. So this is also the classical idea. It obeys the semi-classical ideas. And the most probable distribution of this Bose-Einstein is given by Ni is equal to Gi divided by e raised to alpha plus beta Ei minus 1. And this we are going to derive. And these are called as the bosons. The Bose-Einstein particles are generally called as the bosons. And now we'll start the derivation like this. So consider the derivation is exactly similar to the Bose-Einstein distribution, and slightly some change will be there. So the starting part is same. That is why it is easy to derive all these three distributions since there is some similarity in the derivations. So consider a system consisting of capital N identical indistinguishable particles like photons, phonons, etc. And let n1 comma n2 comma n3 dash 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 ni are the group of particles having energy e1 comma e2 comma e3 dash 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 ei respectively. So the total number of particles in the system is capital N is equal to n1 plus n2 plus dash 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 ni is equal to constant. Let this is be the equation 1. So next we'll move ahead. Next, the total energy. The total energy of the particles is it is equal to E1 N1 plus E2 N2 plus dash 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 EI Ni is equal to constant. So this is also same like the Maxwell-Boltzmann distribution, and here E1 is the constant energy possessed by all the particles present in the N1 group like that. And these equations 1 and 2 are written in simplified form as actually it is n is equal to summation or I ni, and that I am going to differentiate. Then it becomes dn. It becomes dn is equal to summation over I dni, that is equal to 0. because here ni is a constant, therefore it is 0. And similarly, the differentiation of the second equation and writing it in the short form gives det. Det is equal to summation over I ei dni, that is also is equal to 0 because the total energy is also constant. Next, here the particles are identical and indistinguishable, and a cell or state can have any number of particles. So using this idea, just I am telling you, I am giving one example here. So in the figure, 5 states bar cells are made by 5 minus 1 partitions of the box. Here a box is there. This box has 5 partitions. Partition 1, 2, 3, 4, 5. 5 partitions are there. And so our task is to put or fill up these partitions with the particles. So our task is to arrange ni number of in general our task is to arrange ni number of particles among the gi minus 1 cells or partitions. So thus the number of partitions permutations of ni particles and the gi minus 1 partitions is given by ni plus gi minus 1 factorial. But the cells and particles themselves can be arranged in gi factorial and ni factorial ways. So thus, the total number of ways in which n, the total number of particles can be distributed among GI states is given by this formula. This is omega. Omega is equal to product over I GI plus Ni minus 1 for whole factorial divided by GI minus 1 factorial and Ni factorial. Where again this symbol is not the pi symbol, this is the product symbol. And since Ni and Gi are large, we can neglect 1 in the above equation. Thus we write omega is equal to product over I uh, into gi plus ni factorial divided by gi factorial and ni factorial. Then we have to take a log on equation 5. So log omega is equal to log of this whole equation. So this is equal to, when the log operates on this product, it becomes sum. So therefore summation over I in the bracket log of gi plus ni whole factorial divided by gi factorial ni factorial. Next, continue the simplification. Now you apply the logarithmic rules. So using logarithmic rules, it is log of gi plus ni factorial minus log of gi factorial minus log of ni factorial, where we have used log of a by b formula. So log of a by b is equal to log a minus log b, and this is equal to. So here we are applying the Stirling's theorem to expand these factorial terms, because this is log of gi plus ni factorial term is that this has to be expanded using Stirling's approximation. So the Stirling's approximation is that log of ni factorial is equal to n log n minus n. So that is the formula. Using that formula, I am expanding this log of gi plus ni factorial. So this becomes gi plus ni into log of gi plus ni minus gi plus ni. So this is the expansion of this term using Stirling's approximation. Next, similarly, you expand log of gi factorial using Stirling's approximation, you will get these two terms. And similarly, you expand the log of ni factorial using Stirling's approximation, you will get these terms. So here, so this gi plus ni terms get cancelled because of the plus and minus signs, and this is the Stirling's formula, and we write the remaining thing, remaining part. So the remaining part is log omega. Log omega is equal to summation over I gi plus ni into log of gi plus ni minus gi log gi minus ni log ni. And now we have to differentiate equation 6. So differentiating equation 6, we get d log omega. D log omega is equal to summation over I. Differentiation of this using the product rule. You have used the product rule of differentiation. So it is gi plus ni, and this log of gi plus ni is differentiated. It is 1 by gi plus ni into dni. Actually into dgi plus dni, but dgi is 0 as gi is constant, so only dni is written, plus log of gi plus ni into differentiation of this gi plus ni is dni, again same thing. So it is actually dgi plus dni, but dgi is 0, so simply dni is written. So that up to here, from here to here, the differentiation of this term is over. Next, we have to differentiate this term, but this term contains only gi log gi. So gi is a constant, so it is whole a constant term. So its derivation is a 0 minus differentiation of the last term ni log ni. So its differentiation becomes dni log ni. That means ni is differentiated. So it is dni log ni minus ni. Differentiation of log ni is 1 by ni into dni. So these are the terms cancelling. Here you cancel, and dni cancel, ni get cancels. So after cancelling the terms, we are left with this thing. So it's equal to summation over I log of gi plus ni into dni minus dni log of ni. This is the left, this is the thing left with us. So this is the logarithmic formula used. And this summation of dni is common. So take it out, and it becomes log of gi plus ni divided by ni. So this is the equation 7. Next, at steady state, omega is constant, and hence d log omega is equal to 0. So thus the equation 7 becomes summation over I dni and log of gi plus ni divided by ni is equal to 0. And next, that means we are setting this d log omega is equal to 0. So therefore this becomes is equal to 0. So this is equal to 0. Next, multiplying summation of dni by alpha and summation over I ei dni by beta, and subtracting from equation 8. This is the equation 8. We have summation over I dni log this term. So this term is that, and minus summation over I dni alpha I, because we have multiplied this summation of dni by alpha and subtracting. Similarly, this term is multiplied with beta and subtracting. So it is minus summation over I ei dni beta is equal to 0. And continue the simplification. So summation of dni is here and here and here. Take it out and write the equation. And next, you send the summation over dni to the RHS, it goes to 0, and remaining term is this much. And you take these two terms to the RHS side, it becomes log of gi plus ni by ni is equal to, these two terms goes to RHS, it is alpha plus beta ei. And remove this logarithm on LHS side, the RHS side goes to exponential. So it is gi plus ni divided by ni is equal to e to the power alpha plus beta ei. And simplify this one, gi divided by ni plus 1. In taking separating LCM, gi plus ni plus 1 is equal to e to the power alpha plus beta ei. And you take this one to the RHS side, it becomes minus 1. And lastly, rearrange the terms, it becomes ni. So you take ni to this side, and this whole term becomes to the denominator. So lastly, it is ni is equal to gi divided by e to the power alpha plus beta ei minus 1. So in this way, we got the expression for a distribution formula of the Bose-Einstein distribution. Examination point of view, it is very, very important, and prepare immediately. Thank you.